Okay, so let's just recap where we were in the last class. So what we did was we looked at maps between manifolds. Okay, so we had um, a manifold M and a manifold N, and we assume that there's some smooth function f, okay, between these two manifolds M and N. And importantly, M and N need not even be manifolds of the same dimension. Okay, so capital M could have dimension small m, capital N could have dimension small n, and these two could be different. And what we saw in the last class was that there is a natural mapping between the tangent space at a point P, which lives on this manifold M, and the tangent space at the point F of P, okay, where F of P lives on this manifold N. Okay, so there's a natural mapping, and this mapping takes you from a tangent vector here to a tangent vector here. So you can push forward tangent vectors through this transformation F. Okay, and that mapping was called F sub with the lower star. And similarly, we saw that for dual vectors, okay, there's a mapping F upper star, which takes a dual vector at the point F of P and maps it to a dual vector at the point P. Okay, this is a natural mapping induced by F. And we saw that in a particular coordinate system, okay, this mapping is implemented through this Jacobian. Okay, so y are the coordinates on n, x mu is the vector, okay, on at the point P. And so this was the transformation. So this is the Jacobian of the transformation. These are the components of the original vector, and this is the vector that you pushed forward from from M to N. Okay, so this is a vector at some point on N. And similarly, we saw that dual vectors. Okay, dual vectors are transformed. So this is the vector at N. Okay, or in the dual tangent space at F of P on N. This is mapped again through the Jacobian through a dual vector at the point P on the manifold M. So this is called the pullback. Okay, this is the pullback, and that's the pull. And for the vector, it was a push forward. And these can be generalized to arbitrary vector-like indices and arbitrarily dual vector-like indices. Okay, but we saw that in general, you can't push forward dual vectors and you can't pull back vectors. Okay, this is only a one-way transformation, except in the case when F is a diffeomorphism. When F is a diffeomorphism, then you have a mapping from M to N, which is F, but you also have the inverse mapping, F inverse, from N to M. And when you have both of these, then you can push forward vectors, okay, using F, and you can pull back dual vectors also using F. But you can now pull back vectors using F inverse, and you can push forward dual vectors again using F inverse. Okay, so if this is a diffeomorphism, then all of these possibilities are allowed. Okay, and I won't write them down, but we derived in particular coordinate systems, right? What the dictionary looks like. Okay. Okay, so today what we're going to do is we'll start with the concept of submanifolds, and then we'll go on to discuss the idea of flows. Okay, so we had been using submanifolds somewhat implicitly in our previous discussions. So let's formalize the definition of what we mean by a submanifold. So here's a definition. So let F be a map from one manifold M to another manifold N. Okay, so this is some smooth map. But now we're requiring that the dimension of this manifold M be smaller or less than or equal to the dimension of this manifold N. Okay, now we'll give some definitions. Okay, so this is just a map that we're defining. Now, if we have this map, we say that F is called an immersion. Okay, this function defines an immersion of, sorry, not of F, of M into N. Okay, so this is immersing M, okay, and it's dropping the points in M into points in N. So that's what we mean by an immersion. But it must satisfy certain conditions for it to be thought of as an immersion. It's not sufficient that you just have this smooth mapping. Okay, and the important condition is that when I pull forward or push forward, sorry, vectors, Okay, when I push forward vectors in at any point in M, if this is a point P in M, and this is mapped to some point in N. Okay, N is a sort of bigger manifold. It's a higher dimensional space, so it's mapped to some f of P, and we push forward a vector. Okay. Now the important point is that this mapping, which pushes forward vectors, this f star, if this is an injection, that is, it's a one-to-one map. Okay, that is between every vector here, you get a unique vector here. Okay, that is two vectors here will not give me the same vector here. Okay, that's the important criteria. It's a one-to-one map, or another way of saying it is, if I take this vector space, okay, since each vector is mapping to a unique vector here, what is going to happen is that this vector space will map to a vector space here, okay, but this vector space that I map to over here, okay, will be instead of an n-dimensional vector space, it will be exactly m-dimensional. Okay, n dimensions is the full dimension of the vector space here. This is TFP of n. Okay, but you're mapping to an m-dimensional subspace of that. Okay, so this will happen if you ensure that this mapping f star between the vector spaces is one-to-one. Okay, that is, the rank of this mapping is of dimension capital M, which is small. Okay, or in other words, we're saying that the kernel of f star is 0, which means that if I have a non-zero vector here, okay, this is always mapping me to a non-zero vector here. Okay, what can happen, for example, if you imagine a 2D vector space, so imagine something like x, y, and if I map this such that anything which has a y component, okay, gets squished to just having an x component. Okay, when I go to this tangent space over here, then roughly speaking, in that case, this is not going to be an immersion, okay, because I will have multiple vectors with the same x component, okay, but different y components, but they all get mapped to the same vector in this vector space. Okay. So basically, if I'm reducing the dimensionality of the tangent space, okay, and I'm not keeping it maximal, that is of dimension m, then this map will not be an immersion. Okay, but if I preserve the dimensionality of the tangent space, then or I keep the mapping between tangent spaces one-to-one, then what I will get is I will get a one-to-one map. Sorry, I will get an immersion. Okay, so this map is takes an m-dimensional vector subspace. Sorry, an m-dimensional vector space, which is TP of m, and it maps me to an m-dimensional subspace of TFP star n. Okay, sorry, not star, TFP n. Okay, any questions about this?
Sir, how does this mapping ensure that the mapping is from one m-dimensional to another m-dimensional, which is a sub vector space of a bigger dimension?
No, we're saying that this is a definition. So if the map satisfies this criteria, then we call it an immersion.
Okay, so my confusion is that how is it that f star is such that we are going from one m-dimensional to another m-dimensional in n, where I mean n is actually a bigger space.
Where n is a bigger space. I mean, it's like, the domain of a function can be smaller than the range, right? I mean, sorry, can be smaller than the codomain.
Yes.
Right. So I'm mapping. I don't see anything wrong with this, right? I have a tangent space which is of dimension m, and I'm mapping to a subspace of this full vector space. Right?
Yes, sir. So so how does this mapping is ensured? I mean, is it
No. So what I'm saying is, once I know f, okay, then that automatically determines f star. And the claim is this is not ensured by any means. Okay, but if this condition is true, then we call F an immersion.
Okay. So this is the definition.
This is a definition of an
Okay.
immersion. The definition is through F star, but F star is automatically fixed once we fix F. Okay, so F itself defines whether or not this is an immersion. Okay, now now here's another definition. Okay, so now suppose we have this map from M to M, N to N. Now we define an embedding. Okay, we call this map an embedding. If this map F is both an injection, that is, every point P here is mapped to a unique point F of P. Okay, so this map has to also be one-to-one. It's not just the map between vector spaces, which is one-to-one, but it's also the mapping between points, which is one-to-one. Okay, or it's an injection. If this condition is true, that is, if F is an injection and an immersion, that is, F is one-to-one and F star is one-to-one. Okay, then we say that the image. Okay, so this entire this is M. Okay, each point will have an image inside N. Okay, and since in general, since N is a bigger dimensional space, this will only be some part of N. The image F of M is called a submanifold of N. Okay, so this is F of M, okay, which is the image of M. Okay, that is the set of all points that are mapped into N by F. Okay, so that is called F of M. So this image F of M is called a submanifold of N. Okay, so this is called a submanifold. Okay, the conditions for this are that F is one-to-one and F star is one-to-one. Okay, if these two conditions are true, then we get something called a submanifold. Okay, and in practice, this F of M, this submanifold that we're getting, is actually going to be diffeomorphic to capital M. Okay, in practice. Okay, that these two will actually turn out to be diffeomorphic to each other. Okay. So this is just a definition. Okay, so we've defined an immersion map and we've defined what we mean by an embedding. Okay, F is an embedding, and this image is called a submanifold. If F is an embedding, then this image of F is what we call a submanifold of N. So let's just look at some examples and it'll become clear. Okay, so let's take a simple space M. We'll take M to be an S1. Okay, that's something that is topologically a 1D circle. And so consider these points A and B on the circle. Okay, and consider this point P. And this map F takes us into the topological space R2. Okay, which is N. Okay, sorry, the manifold N. N is R2. Okay, again, these spaces have no metric on them. Okay, they just have these are just topological spaces which are topologically locally like Rn. Okay. Okay, so now the point. So now imagine that this circle is mapped to a figure 8. Okay, like this, and what is happening is that this point A. Okay, you start at A is this point. A is mapped to this point, and this is F of A. Okay, then as you go around the circle, as you go around the semicircle, you basically end up covering this whole circle here. Okay, so this point also becomes F of B. Okay, and then as you cover the rest of the semicircle, okay, you now cover the lower half of this figure 8. Okay, and then you come back to A, which brings you back to F of A. Okay, so this is a map. Okay, this defines a map. Okay, it's easy to see that this is a smooth map. Okay, and this map is an immersion. Okay, why is it an immersion? Because if you look at the tangent space on M, for example, if I look at the tangent space at A, the tangent space on A is defined as a 1D vector space. Okay, so it's a 1D vector space defined by, I can think of it as tangents to the circle. Okay, but really it's just a tangent space defined through this partial theta. Okay, if theta is the coordinate. on this. Okay, these are basis vectors. Okay, in this coordinate system. Okay, and these are being mapped to vectors in the tangent space at n, which are again one-dimensional vectors. Okay, this is a 1D subspace of TF of PFN. Okay, so and this 1D mapping is always present. Okay, so that means at A there is a mapping to the tangent space at f of A. Okay, and at B there's a 1D mapping to the tangent space of f of B. Okay, there's no conflict there. But these are different 1D subspaces. Okay, so these are different 1D subspaces for P is equal to A and P is equal to B. Okay, because that I'm thinking of, okay, at A. Okay, so this vector is getting mapped to something which is sort of, you imagine, tangent to the figure 8 like this. Okay, and it's this 1D subspace. Okay, now in general, if I think about R2, okay, I have a 2D tangent space at any point. Okay, so at this point I have a 2D tangent space. So the same point I can have, I have a bigger tangent space. Okay, but when I'm doing this mapping from the tangent space or tangent vectors at this A to the tangent vectors at f of A, what I'm doing is I'm picking out a 1D subspace of tangent vectors. Okay, I'm picking out a 1D subspace of tangent vectors. And similarly, when we come back to B, we're picking out a 1D subspace of tangent vectors, but this is a different 1D subspace. Okay, so we're picking out different 1D subspaces, but locally this is always yeah, but locally this mapping is 1-to-1. Okay, that means at A there's a 1-to-1 map between tangent vectors here to this subspace, and at B there's a 1-to-1 map between these vectors and this tangent space. Okay, so this map is an immersion. Okay, however, this map f of S1, okay, this mapping is not an embedding. Okay, and therefore this f of S1 is not a submanifold of R2. The reason it's not a submanifold is because f star is 1-to-1, but f is not 1-to-1. Okay, because A and B are mapping to the same point here. So this map would be called an immersion, but it would not be called an embedding. Okay, it's not an embedding map, and therefore this figure 8, okay, which is f of S1, is not a submanifold of R2. Okay. However, if we had just taken a circle and instead of trying to be clever and make this figure 8, we map each point to a unique point here. Okay, then this map G, okay, which let me call this G, even if it's some distortion of the circle. Remember, again, there's no metric, right, to tell you that the distances are distorted. There's no way to tell that. This G is an embedding. Okay, it's an immersion, and it's also a 1-to-1 map. Every point is mapped to a unique point here. So then this G of S1 is a submanifold of R2. Okay, so this map G is said to be an embedding. It's an immersion and it's a 1-to-1 map. And G of S1 is a submanifold of R2. So every embedding is an immersion, but not every immersion is an embedding. Okay. Okay. So now I'll give you an example which we've been using many times. Okay. So we map. You can map spheres Sn. Okay, into Rn plus 1, and in particular the one that we've dealt with the most is taking a 2-sphere and embedding it in R3. Okay, so now you get a formal definition to what it means to embed something. So we think about a 2-dimensional sphere. Okay, so usually it's shown like this to indicate that it's the surface of a ball, and now we embed it inside, let's say, we take a mapping of this sphere, okay, in some very natural way to points on a unit sphere, let's say in R3. Okay, so this S2, which is here, is diffeomorphic to its image, which is f of S2, okay, which is the embedding in R3. Okay, so normally when we're thinking about this S2, we're always actually thinking about this embedding, right? We're thinking about the surface of a ball as embedded in 3 dimensions. But really, the 2-dimensional sphere has an independent existence as an abstraction. Okay, as in it doesn't have to exist in 3-dimensional space, as an embedding in 3-dimensional space. In GR, we're taking this philosophy to its limit, right? In the sense that we're not necessarily talking about embeddings. We're just talking about manifolds themselves without worrying about their embeddings. Okay, so this embedding gives us a nice way to visualize curvature, but it's not necessary, okay, to define curvature. Okay, so how do we get curvature out of this? Well, what we need is a metric, okay? And what we've seen is that if I have a smooth mapping, okay, if I have a smooth mapping from here to here, okay, this is a smooth mapping. Okay, this is not a diffeomorphism, right? Because I'm only mapping to a submanifold of this R3. Okay, so F is not a diffeomorphism. Of course, if I restrict myself only to this image of S2, then it is a diffeomorphism. Okay, but on the full R3, it's not a diffeomorphism. So now in R3, I have the natural metric. So supposing I take my Euclidean metric, that is G mu nu is 1, 1, 1. Okay, so I have a metric. And now what I can do is, since I have this map from M to N, okay, we saw that dual vectors or tensors which are made up of only dual vector type indices can be pulled back, okay, which means that you can pull back G mu nu to obtain a metric G prime mu nu on this two sphere. Okay, so you can get the induced metric. Okay, so this would be called the induced metric from the embedding. Okay, so if you give me a metric on R3, that is, let's say I take a standard Euclidean metric, this will induce a metric on this S2. Okay, and it's defined by this pullback. So in a particular coordinate system, the metric on S2, if I want to work out the components, will be related to the metric on R3 times these Jacobians. Okay, these Jacobians, you have to be careful. This Y is the coordinates on the R3, X is the coordinates on S2. Okay, and this Y are three-dimensional coordinates, which means alpha and beta run over 1 to 3. Whereas this mu runs over only two-dimensional coordinates. Let's say mu runs over only theta and phi, okay, which are coordinates on this S2. And so now I need to define what is the dictionary of this mapping, okay, of from X into Y. Okay, and so if we use polar coordinates, okay, so alpha beta is 1 through 3, or let's say we use r theta phi. Okay, then our metric G in R3 is G alpha beta dy alpha dy beta, which is dr square plus r square d theta square plus r square sine square theta d phi square. Okay, so Y has this r theta phi coordinates, X, which is the coordinates on S2, has only theta phi coordinates. And without loss of generality, we'll assume that our embedding is such that we're restricted to r is equal to 1. Okay, so some particular sphere of some size. Okay, then we can work out, okay, for example, suppose we want to work out G prime theta theta. Okay, so what we need to do is take G alpha beta, which is this metric, which is the metric in R3. Okay, we need to focus only on those points which are in the image of f of S2. Okay, that is, we're focused on the points with r is equal to 1. And then what we need to do is we need to apply our Jacobian. Okay, we need to apply these Jacobians. Okay, and this Jacobian can be thought of now in matrix notation. It can be thought of as, let me take Jacobian transpose, Jacobian, and G alpha beta, where this Jacobian is with respect to a particular mu nu coordinate. So for example, if I'm working out G prime theta theta, okay, this Jacobian has an index alpha, okay, and an index beta. And it has indices mu nu, which are fixed to theta theta. Okay, so that means I'm taking derivatives with respect to theta. Okay, and this is, let's say, the alpha index, and this is the beta index, which runs over r theta and phi. Okay, so it's something like this. So it's this matrix element that I need to evaluate. Partial r, partial theta, partial theta, partial theta, partial phi, partial theta. Then I have the metric, okay, which is G alpha beta. This is the metric on R3. Which is 1 r square sine square theta, partial r, partial theta, partial theta, partial theta, partial phi, partial theta. And at the end of my evaluation, I will set r is equal to 1. Okay, an important thing to do is you set r is equal to 1 not before you evaluate these derivatives, but after you evaluate everything. At the end of the calculation, you set r is equal to 1 to restrict yourself to the sphere. So if you evaluate this, okay, partial r, partial theta is 0, partial theta is 1, partial phi, partial theta is 0. Okay, so what I'm going to do is, again, I'll get only 1 here, so I'll pick out this element. Okay, so I'll just basically get r square. And at the end of the calculation, I set r is equal to 1, so I get 1. So G prime theta theta will be 1. And similarly, you can work out the other components and you'll find G prime phi phi is sine square theta, G prime theta phi is 0. So what you'll get is ds square is d theta square plus sine square theta d phi square. Okay, so this is what we kind of expect is the metric on this two sphere. Okay, but it's nice to see how this emerges by using our formula for this Jacobian and using the pullback of G mu. Okay, pulling back the metric. Okay, yeah. Any questions about this?
Sir, like about this R is putting R is equal to one thing, like this map F is defined from S2 to R3, like whole of S2 to whole of R3. So in that there is no restriction, right?
No, again, when you say whole of S2 to whole of R3, it means this mapping can take you to any point in R3, but
Yes.
the particular map we have chosen takes us only to the points with R is equal to 1.
Okay.
Right? I could have distorted it. For example, I could have mapped this to some kind of ellipsoid. That could have been a different choice of F.
Okay, so F is such a map that it only like it takes us from S2 to R3, but within like with a distance of 1, like in R3.
With a distance of 1.
By
No.
in the radius 1. Okay.
Yeah, so this is a particular choice we are making for this map, yes.
Yes, we cannot say distance because we don't have metric, but I mean R is equal to 1 with the radius 1.
Yeah.
So f of S2 is diffeomorphic to S2.
F of S2 is diffeomorphic to S2. So submanifold is always diffeomorphic to the original manifold.
Yeah, and that is why we're setting R equal to 1 at the end.
Yes.
Okay.
Well, also I could have chosen different coordinates, right? The theta phi here need not be the same as the theta phi that I'm choosing in polar coordinates here. Right? I could have chosen other coordinates to define this as 2. It's just convenient to do so because we know what the answer will be. Okay, so this idea, I mean, so very naturally, we had this idea that what we'll do is we'll set R is equal to 0, R is equal to 1. And what we did was essentially to kill off this dr square, set R is equal to 1 here and set R is equal to 1 here and argue that that was the metric on S2. Okay, and that is perfectly fine. And it's actually equivalent to this procedure, but this procedure is more general. Okay, for the prescription that we've given, it works for any coordinates. Okay, that you assign on the S2 to any coordinates that I map to on the R3. Okay, we can always pull back any metric. Okay, once we have this kind of embedding map.
Sir.
Yeah.
How do you put these G menu prime and G menu things in the matrix form?
Oh, so what I did was I said, so of course it's this. G mu prime is G. So this is the index form. Okay. Then all I did was to define a matrix G alpha beta. Okay, in R3, where the entries of this matrix are for alpha beta is R theta phi. So these are, let's say, the alpha values, and let's say the beta values are again R theta phi. So now I give you the entries of this matrix. Okay, and they're easy to find from here. So this is the entry of GRR. The coefficient of GRR is 1. So that goes here. The coefficient of G theta theta is R square. So that goes here. The coefficient of G theta phi is R square sine square theta. So that goes here. All other entries.
But I'm asking that you have put one part GY beta, one row one side, then metric is sandwiches between these two.
Okay. Okay, good. So this G prime mu nu. So I fixed mu and nu. Okay, so I fixed them to be theta theta. I fixed this to be theta and I fixed this to be theta. Okay, so this partial x theta, by that I mean on the S2, the coordinate is theta. Okay, so now this has only one free index, which is alpha. This has only one free index, which is beta. Okay, and I'm summing over the alpha beta indices. So now this looks like a matrix product, okay, with basically it's like a matrix dotted with a vector, one index. So this is, let's say, the alpha index, which is the uh, row index. Actually, this I should think of as beta, and this I should think of as alpha. Okay, alpha is, let's say, the row index, and so I can think of it as being multiplied by this row vector. Okay, something like that. V transpose. Because at the end I just get a number. Okay, once I sum over all the alpha and beta. So basically, it's of the form Mij xi xj. Okay, and this I can always think of as matrix times a column vector. Okay, is this. Okay, this product is like a matrix product, and this product is also like a matrix product with a transpose. Okay, in general, if I had written something different here, okay, then this would be y transpose mx.
And sir, once we have defined the metric on the manifold, then we can pull back not only the dual vector but also vector, because we can transpose our vector to del vector using the metric, and then there is no need to differentiate between, like, we can only uh, pull back the dual vector in case we have defined the metric on manifold. Can we do it for always, or
Uh, you're saying that once I have a metric, then so the metric induces a mapping from vectors to dual vectors. And now if I can pull back a dual vector, so these are on an n. Okay, this mapping is induced by the metric. And now if I have a dual vector, I can pull it back to a dual vector on M. This is a dual vector on N, which got pulled back to a dual vector on. And now in particular, I can pull back the metric also.
yes.
And if I can pull back the metric, then I can also get a dual vector from this, okay, because I have a metric and I have a dual vector, so I can construct from these two a vector. Okay, and this is all on M. So yes, that can be done. Okay, and the secret reason that this can happen is because this S2, if this is an M, okay, important caveat is that this map has to be an embedding. Okay, if it is an embedding, then this map between these two is 1-to-1, and then this is a diffeomorphism. Okay, and if it's a diffeomorphism, we know that you can always pull back vectors as well as dual vectors. Okay, so what should not happen is that this map is an immersion map, because then I think you will run into a problem. Sorry, if it's not an immersion. Sorry, if it's not an embedding. Okay, so let's say, like the previous example, if we had this figure 8, then I think you might run into a problem, but I'm not sure.
Yes, I think at the point where A and B map to the same point, at that point we cannot define.
I think you can define it locally if it's an immersion. Um, Yeah, okay. I think it's fine. I mean, there's a subtlety, but let's not get into it. Okay. Basically, I'll just say briefly. The idea is that there are two different ways to construct the vector here. One is by pulling back a dual vector, pulling back the metric, okay, and then using this metric to raise the index of the dual vector to get a vector. Okay. The other way is if there's a diffeomorphism between this and its dual map, then you can directly take a vector here and push forward using the dual map. You can get a vector here. Okay. So these two will agree. Okay. These two methods of constructing the vector here will agree. Okay. They will not agree, obviously, in the case where this F inverse is not defined. Okay. And this F inverse is not defined if the map is not an embedding. But this procedure for constructing the vector will still work through the dual vector and the metric and the pullback of the metric. Okay. Yeah, so let me just give you one quick example of a non-immersion map. So if I take this circle and I map it to a point, okay. Now what I had was a 1D tangent space, and now this 1D tangent space gets mapped to a 0D tangent space, which means it gets mapped to, let's say, 0. So basically I had a 1D tangent space, which I mapped to a 0 vector, okay, here. And so I reduce the dimensionality of my tangent space, okay, when I did this mapping. So that becomes a non-immersion map. Okay, or the kernel of F star is non-zero. It's not just that the 0 vector gets mapped to the 0 vector here, even other vectors get mapped to the 0 vector. Okay, and so it's a non-immersion map. In general, if I'm doing this mapping from M to N, even if N is higher dimensional, I could always map this mapping so that I map M to a lower dimensional subspace. So if this is M, this subspace F of M could be, some, let's call it K dimensional, and K can be less than M. Okay, and if K is less than M, then basically I'm going to reduce the dimensionality of the tangent space, and then it would become a non-immersion map. Okay. Anyway, these are all kind of cases that typically we're not going to be interested in GR. We're only going to be interested in kind of submanifolds. Okay. So immersion maps, which are also one-to-one. Okay. Any question? Any more questions?
Sir, in the first example, like which was immersion but not embedding, uh, there like sir, like the way you define the tangent space in R2, like the subs, that was like taking tangent vectors in two directions, like this. So, but like this is sort of an image, but like, is it possible to mathematically construct F star so that like we can see from maths that we are getting from 1D vector 1D vector space, we are getting a map to another 1D space. Like this is like an image.
Yeah, because if you think about how we define vectors, right? We define vectors by thinking about curves on this manifold.
Yes.
So the curve on this manifold has to lie along this this immersion, right? So the curve has to be defined like this, which means the tangent vectors are defined along this curve, right? So they are literally what I drew.
Yeah. Yeah. Okay. Yes.
Okay. Okay, so the next thing is today what we'll do is we'll talk about the idea of flows. Okay, and here's the basic idea. So let's consider a manifold M, okay, with a vector field X. So again, there's no metric. Okay, there's just a manifold with a vector field. Okay, so this is the vector field X. So at every point, in particular this point P, has some vector X at P associated with it. Okay, so every point I've drawn many vectors. Okay, so every point has some vector associated with it. Okay, this is a smooth vector field. So now the claim is, okay, so this is a claim. which is that if you're given a point P on the manifold, that is, I'm given this point P, then there is a unique curve C of T, okay, which passes through P. There's a unique curve which passes through P, such that the tangent vectors to this curve, okay, that is all the tangent vectors to this curve. Okay, I've not drawn it very well, but okay, so all the tangent vectors to this curve. So these are tangent vectors. All the tangent vectors to this curve are which are denoted as T of T. Okay, so which means if there is some T from A to B, okay, given a value of T, I map to some point on this pink magenta line. And at each point, given a value of small t, I'll tell you which point I'm at, and then I construct the tangent vector to this curve. That's T of T. Okay, so that is a tangent vector. This tangent vector T of T is identical to X, okay, the vector field at that point. Okay, so X was a vector field which was given to you. Okay, so if I'm given a vector field X, okay, then the vector field X agrees exactly with these tangent vectors. Okay, so there is a unique curve that I can construct which passes through P such that the tangent vectors to this curve exactly match the X's at those points along the curve. Okay, that's the claim. Okay, so so this is exactly what I was drawing. So we have a map from A to B, which is parameterized by T, and you define a curve, which is a map from this interval to a curve on the manifold. And what you're now saying is if I have tangent vectors T of T to this curve, these tangent vectors exactly agree with the X at those points along the curve. So for this point, the tangent vector agrees with the X here. For this point, the X agrees with the tangent vector here. For this point, X agrees with the tangent vector here, and so on. Okay, so in other words, the tangent vectors match the vector field that we were given on the manifold. And if we find such a curve, this curve, so first of all, the claim is that this curve exists and is unique. The second is that such a curve C of T is called an integral curve in M. Okay, this is the name that we give to such curves. Okay, they're called integral curves in M, and this is an integral curve on M passing through the particular point P. Okay. So is the claim clear? The idea of the claim, we'll prove this claim next.
Sir, like while defining vector space, we have already mentioned that there should be those equivalence class of curves. So this C of T should always exist. So why is this a new claim?
The C of T should always exist. No, but look at what you are given. You are given a manifold and a vector field. Okay, I'm not specifying a curve.
But this vector field has to come from some curve only, because that is how we define vectors.
Yeah, but those are locally, right? Locally, you're right. Okay, in the sense that locally we're defining the vector here by defining a curve through this point.
Yes.
Okay. Now what we're saying is, so this will give me a particular vector. If I take another curve, I will get another vector. Okay. In fact, there are many curves which give me the same tangent vector, as you correctly pointed out, right? There's an equivalence class of curves which have the same tangent vector at this point P. Okay. So many curves which have the same tangent vector here. So let's call these C1 and C2. Okay. But now what we're claiming is that there is a unique curve. So out of this C2, C1, many others. Okay. There's a unique. So of course, I choose it so that the curve has tangent vector xp. But even within that, there are many curves which are possible. Okay. So which of these curves am I picking? I'm picking a curve such that not just at this point P, but at every point along the curve, the tangent vectors match the vector field X.
Yes, sir, because it's a field and not just a vector defined at a point. So
it's not just a vector.
Yeah.
Okay, which means that basically at every point, I am kind of going with this curve, okay, which is tangent here. And again, I have many choices for what I can do later. But the choice of what I can do later along this curve is determined by the next, tangent vector at a nearby point, and so on. Okay, so essentially this gives a picture of what we're trying to do. What we're trying to do is essentially write this vector field. Okay, so we follow this vector field by thinking of these as tangents, and we follow these tangents. Okay, so we follow these tangents, and there's a unique curve which is following all these tangents, and that is called the integral curve. So once I specify the initial point that I start with, there's a unique field which is going to write these tangents, okay, and sort of flow along these tangents.
Sir, and this curve is defined throughout the manifold.
This curve is defined throughout the manifold.
So is it a kind of like magnetic field lines for each point we can define a tangent vector which denotes the direction of magnetic field itself?
Yeah, exactly. That's I mean we'll show something like that. These are like it's very similar. Okay, and I would think of these more as streamlines in the sense that think of this as a velocity field, okay, which is telling you which direction to flow. And this streamline is sort of, if I have a test particle and I let it flow in this with this velocity field, okay, it'll kind of ride this curve. Okay, so think of streamlines in a wind tunnel, for example, right? This would be the idea. Okay, so let's prove this claim now. Okay, so let's suppose that in a particular so we'll do this in a particular coordinate system. Okay, so let's take a particular coordinate patch U. Okay, and this curve C of t gives us points Q. Okay, so U is basically a coordinate patch. So if I have my manifold M, I have a coordinate patch U, and there's a mapping psi, okay, which takes a point Q here and it assigns it coordinates x mu. Okay, of t because I'm assigning Q to be on this curve. Okay, so these are the coordinates associated with points on this curve. Okay, so for given t, I will have to specify all the x mu coordinates to get the coordinates of that point on the curve. So now the tangent vectors, okay, once I assign this coordinate system, okay, the tangent vectors can be found as dx mu dt partial x mu. Okay, this we've seen before. If you have a curve, then the coefficients, okay, are dx mu dt, and in where these are the basis vectors. Okay, and this is evaluated at a point x. So these are the tangent vectors, and so these are the tangent vectors. So if you give me the curve C of t, it is equivalent in coordinates to specifying x mu of t. Okay, all of these x mu of t, which means you're giving me all these derivatives, which are nothing but the components of t mu. Okay, so given a curve, I can construct this tangent field t, and I can also, I'm already given a vector field x, okay, where x is some x mu, at which point, at the points along the curve, evaluated at x of t, partial x mu. Okay, again at a particular x. So this is given to us. Okay, so this vector field is given to us when we specify x, and these coefficients are smooth functions. Okay, so these are smooth functions. And now the claim is that this tangent vector field and this x, these are the same at all points along the curve. Okay, so this tangent vector field is the same as x, which means that these basis coefficients are exactly the same. Okay, or dx mu dt is equal to x mu of x of t. So where mu runs from 1 through n, where n is the dimension of the manifold. Okay, so you are given this right hand side because you're given what this field is. Okay, well, you're given x mu at arbitrary points in the manifold. If you specify a path, okay, that is, you specify this x of t. By x of t, what I mean is you specify the coordinates x nu of t. Okay, for nu is 1 through n. You specify which point I'm at. Okay, I'll tell you the vector field x at that point in coordinates. And then what you have to do is you have to construct a curve c of t such that the tangent vectors to that curve satisfy this equation. Okay, where the tangent vectors have dx mu dt as their coefficients. And so this is one condition that must be satisfied. Okay. The second condition that must be satisfied is that the curve passes through a particular point P. So we'll assume that this point P also belongs to our coordinate patch and it has some coordinates x0 mu. Okay, so x0 is referring to the point P. So we're given that x mu t is equal to 0 without loss of generality. Okay, we'll assume that at t is equal to 0, the curve passes through P and therefore it has coordinates x mu 0. Okay, so now we have to solve this differential equation. Okay, what we want to do is find the curve, which means that we need to find x mu of t. Okay, so we want to find this curve which satisfies this differential equation, which is a first order differential equation. Okay, but these are first order coupled differential equations. Okay, where the right hand side is smooth. Okay, that the right hand side is perfectly smooth, and this x mu. So why is it coupled? Because this x mu I have to solve for x0, x1, dot 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 xn, and the right hand side can depend on all of them in general. Okay, x0, x1 through xn. So these are first order coupled differential equations, n coupled differential equations, PDEs, and we have n initial conditions. Okay, that is that you have to pass through the point x0 mu. So we need to solve these n first order coupled PDEs with n initial conditions, where the dimension of the manifold M is this n. Okay, and by the theory of partial differential equations, the solution always exists and is unique. Okay, which means that this integral curve can always be constructed. Okay, at least locally within some coordinate patch U. Okay, so within a coordinate patch, it's always possible to construct such an integral curve. Okay, so now if I have one integral curve within this coordinate patch, and then I have another overlapping patch, then in this patch I can continue the integral curve. And again, by this theorem, we show that the integral curve is unique, so that the integral curve here has to match, and therefore I can continue on my integral curve. Okay, so I can always continue to build this integral curve, okay, in over the entire manifold, independent of my coordinate system. Okay. The only thing that you have to be a little bit careful about is this t, okay, belongs to, okay, in general, when we parameterize a curve, we say it belongs to some, this parameter t belongs to some range a to b. Okay, and the question is, can we extend this range to cover the entire rail line? Okay, if we can, then we say that there is a maximal extension of the integral curve. Okay, the parameters can be extended up to infinity. And there is a theorem which we're not going to prove, which is that if M is a compact manifold, okay, then the integral exists for all t belonging to R. The integral curve exists. Okay, and that is, you can always find this maximally extended integral curve for a compact manifold. Okay, in general, we're not going to be working with compact manifolds, but we'll assume that, okay, you can get these kind of extensions. Okay, so we'll assume that all our integral curves can be maximally extended. Okay, and this is what I said earlier, that if we stitch together the unique integral curves in different coordinate patches, then this gives us the unique integral curves on the full manifold. Okay, any questions here?
Sir, isn't the differential equation ordinary differential equation?
Oh, sorry, yes, they're not PDEs, these are ODEs, coupled ODEs, yes. Thanks, because I'm only differentiating with respect to t, where t is this parameter. Yeah, sorry, they're coupled ODEs.
So the theorem that you mentioned holds for ODEs?
Yes, it holds for ODEs.
Okay.
if I have n first order differential equations, then I need n initial conditions to solve them. Okay, assuming that everything is smooth, which we are assuming here. Okay. All right. So now we'll come to this idea of a flow. Okay. So I have a manifold M. I have this vector field X. Okay, and I have a point P. Now let sigma pt be the integral curve of X which passes through P. Okay, at t is equal to 0. So there is some curve, a unique curve, which exists, which passes through P. Okay, and therefore at P it has tangent vector. Whatever is the tangent vector at P is going to be the tangent vector to whatever is the field X at the point P is also going to be the tangent vector to this curve. Okay, and there's a unique curve which passes through this such that its tangent vectors are always elements of X. So this curve is called sigma pt. Okay, and we'll denote the coordinates along this curve as sigma p mu t. Okay, these are the coordinates along the curve. So instead of talking about x mu of t, this is the coordinates when I'm at the point t along the curve. This is the muth coordinate, and this is a curve which passes through P. Okay, but remember that only I'm assuming, let's say at t is equal to 0, I'm at P, but at other values of t, I'm not at the point P, I'm at some other point along this curve. Okay, so we'll assume that P has coordinates x0 mu. Okay, if that is true, then if we denote sigma mu p t as sigma mu, we'll denote it as sigma mu t. And instead of putting the P outside, okay, we'll put the P inside. Okay, so just to remind us that this curve passes through x0. Okay, or x0 nu. Okay, where I have taken the full set of x0s. Okay, that's why in shorthand I write it as sigma mu t x0. Okay, so this is the curve. This is the curve which passes through x0. We are now at the point t along this curve, which need not be at x0. Only if t is equal to 0, then I'm at x0. And my coordinates are sigma mu, okay, where mu runs from 1 through n. Okay, so then the sigma mu must satisfy this equation, that is d sigma mu t x0 dt is equal to x mu of sigma t x0. And it has this initial condition. Okay, so I'm just rewriting what we wrote before, just using this notation. Sigma mu at t is equal to 0, x0 is x0 mu. Okay, so these are the n coupled ODEs, and this is the initial condition. Okay, for a single point P in this manifold, okay, we have a curve C of t such that sigma 0 is that point P, and the tangent vectors are these x. Okay, x evaluated at the point sigma t. Okay, now this curve itself is a map, okay, from real numbers, which are the values of t, okay, to the manifold. Okay, that is, the curve is a map from real numbers, okay, specified by t, to a curve on the manifold. Okay, so this is sigma pt, and this curve passes through P. Okay, now you can construct this map, and by the theorem we've shown above, this is a unique map. Okay, so given any point P, so another point Q, there's a unique integral curve. Okay, so for every point P belonging to M, we can construct this integral curve. Which means I can think about, instead of writing this as sigma pt, I can think about this as sigma tp. Okay, I mean, I'm just pulling the p inside because the sigma depends not only on the parameter t. The parameter t tells me where I am along this curve. The parameter p, or the point p, or the point q, tells me that this curve passes through the point p or it passes through the point q. Okay, so for different p's in general, I'm getting different curves. Okay, and it's a map from this t takes values in real numbers. Okay, and this point p takes values on the manifold. So this is the initial point which we called x0. And this is a map from points on the manifold and real numbers to other points on the manifold. So if you give me a P and you give me a value of T, I'll tell you a new point on the manifold that I'm at. Okay, it'll return a new point on the manifold. That is, I find the curve which passes through P, I move by an amount T, okay, and I get a new point on this manifold. That's called a P prime. Okay. If you had given me a point Q, then I would have moved an amount T along this curve and I would have found point Q prime. Okay, so if I change the point P, then I get it's a different map. Okay, so this I can now think of as a family of integral curves instead of just one curve, okay, which passes through one specific point P. It's a family of curves where I can choose which point I choose to pass through, okay, whether it's P or Q or something else. Okay, so this map sigma TP is now called a flow. Okay, so this is the definition of what we call a flow. It's a flow generated by a vector field. So the important point was that I needed to start by specifying a vector field, a smooth vector field on the manifold. Okay, so what you had to give me was a manifold and a vector field X. Once you give me this manifold and the vector field, there is a unique map sigma TP, okay, which I can obtain. Okay, so the sigma is unique. Okay, if you specify the point and you specify how far I move along the curve, I can give you a unique X specifies uniquely what this curve will be. Okay, and therefore it uniquely specifies a flow. Okay, so the rule satisfied by the flow is there's some rules which must be satisfied by this flow. So if I start with the point P, okay, and if I move by an amount S, then I'll end up at some point, let's say Q over here. Okay. So this is sigma SP, that is I move by an amount S and I started at the point P. And similarly, if I say I move by an amount T and I end up at the point, but I start at the point Q rather than starting at the point P. So I move an amount S and I move here. And if I start at Q and I move an amount T, then I end up at R. Okay, so that is sigma TQ. Now, an important rule that has to be satisfied, okay, for this kind of flow is that the sigma TQ, okay, should be equivalent to starting at P and moving by an amount S plus T. Okay, so which means that it should be the same. So this is sigma of T and Q is nothing but sigma SP, which is this. Okay, but this should be the same as starting at P and moving by an amount T plus S. Okay, so this composition map composing two flows, okay, should yield a flow. So composing a flow by an amount S and a flow by an amount T should yield a flow by an amount S plus T. Okay, and this property can, I mean, you can see this quite easily from the uniqueness of the ODEs that our maps will satisfy this property. Okay, maybe I'll skip over that proof. Okay, but you can understand easily why this would be the case. Okay, given the uniqueness of these curves, okay, this map sigma TP will satisfy this additivity property. Okay, if I add the parameters T plus S, then this relationship will be true. Okay. Okay, so here's the theorem. Okay, so if I start with any point X belonging to M, so this was like our point P, then there exists a differentiable map sigma, okay, from R, sorry, no, not this. Okay. So given a vector field X, a smooth vector field X on M, there exists a differentiable map sigma from R cross M to M. Okay, that's the theorem. Where sigma 0x, okay, is equal to X. And this is for any X where this X belongs to a point in the manifold. And T goes to, if you give me a value of T, then I can construct for you sigma Tx, where sigma Tx is a solution to this differential equation. D sigma mu dt is equal to x mu but is x mu is evaluated at sigma Tx with this initial condition. sigma mu 0x is equal to x mu. So I've changed the definition of the point P. I've now assigned it a general, now I allow the point P to be any point on the manifold. So instead of assigning it, this particular coordinate x0, we just write its coordinate as x, okay, or it has coordinates x mu. Okay, and also the third property of this composition map sigma is that sigma, if I start at x and move by an amount t plus s, that should be equivalent to starting at x and moving by an amount s, followed by moving by an amount t. Okay, the second composition map. So this flow can now be thought of as a stream flow. Okay, that is, if I start at the sigma mu tx, okay, what it gives me is you can think of it as a flow, like some kind of liquid flowing, and the sigma mu tx gives the coordinates or the location of a fluid element at time t, where the initial condition is that this fluid element was here. Okay, it was at some x mu. So at t is equal to 0, it had coordinates x mu. And if you tell me a time t later, where is this? It's at sigma mu t of x. Okay, so this is sigma mu t of x. Okay, and this point is uniquely defined. Okay, so where it will be at a later time is automatically defined by the flow. And the flow itself is specified when you give me the vector field x. Okay, so giving me the vector field x, okay, specifies the flow. And so given an x, I can construct sigma, okay, where sigma is a function of t and x. This depends on the initial point, and it takes sigma is a map which takes two parameters. It takes an amount of flow, or you can think of it as the time of the flow. Okay, time I use, in quotes, it's a parameter along the curve, and x is some initial point. Okay, so given an x, I can construct this sigma. Okay, and this sigma, what it does is if I feed it these two inputs, it will tell me where I will end up. Okay. Okay, and this x mu, okay, this x mu that you have to specify to construct the sigma, those x mu's are basically you can think of them as the velocity vectors of the fluid. Okay, so because it gives me x mu is related to the tangent vectors, which is d sigma mu dt. So this really you can think of it as the rate of change of coordinates. Okay, this x mu is related to the rate of change of coordinates. So in some sense, you can think of it as the velocity of the fluid element that started at x at t is equal to 0 and is now at sigma tx. Okay, so this x is really, you should really think of it as a flow field, like some kind of velocity field. And these integral curves are streamlines of the flow. Okay, so let me give you an explicit example to make this clear. So let's take M to be R2. Okay, so M is the manifold R2 on which I can assign the coordinates x and y. And I'll give you this vector field x, x, y. So it's given by minus y partial partial x plus x partial partial y. Okay, and if I try to represent this in a diagram, okay, I will give you something like this. Okay, so this, you should only think about the directions of this flow and not the magnitude, because to construct the magnitude of such a vector, right, the magnitude of such a vector requires you to have a metric. We don't have a metric. Okay, this manifold. So let's only focus on the direction of this vectors. Okay, so the directions of these vectors are like minus y partial partial x plus x partial partial y. Okay, so it's sort of, you can think of this as up to an overall magnitude. Okay, well, okay, you can sort of work this out. Okay, you'll see that it kind of, this is the directions, okay, of the of x. Okay, if I plot the directions of x on this plane. And then you can show, okay, again, I won't do this, by solving those differential equations, that if I start at some point, okay, with some point with initial values x and y, okay, and then I follow this flow for an amount t, then I will end up at a point, okay, which is rotated by an angle t, okay, such that my new coordinates, which are x prime, y prime, will be, or let's to be consistent with the notation, my new coordinates are sigma upper x at t, starting when I started at the point xy, okay, and sigma upper y t when I started at the point xy. Okay, so given that I started here, I can tell you where I end up, and there's a unique sigma, okay, given this vector field x. And you can show by solving those differential equations that you would get something like x cos t minus y sin t, x cos t plus y sin t, which would exactly be what I told you, which would be rotating this point by an angle t. Okay. And this would be the integral curve. And so the integral curve would be the points which are connected. So if I connect all the points for all values of t, what I would get is basically a circle. Okay, so that's the curve. So this magenta curve is one integral curve. This red curve is another integral curve. Okay, and this point by itself is an integral curve. It doesn't flow. Okay, it's a fixed point of the flow. Okay, so and this arrow, the direction of the arrow is showing you the direction of increasing t. Okay, so as I increase the parameter t, this is the way I flow along this curve. So really you can think of it as a streamline, right? It's kind of easy to visualize now. Okay, this is like a rotating, swirling fluid. Okay. And this particular flow that we've constructed is periodic, which means that if I move by an amount t is equal to 2 pi n, okay, then the angle changes by an integral multiple of 2 pi, then I would come back to the same point xy that I started with. Okay, so even if though I flowed by an amount t, I could come back to the same point. And this particular point 0, 0, we've already discussed, is a fixed point of the flow. Okay, that point doesn't flow. Okay, any questions here?
Sir, as sigma is unique, so these curves will never intersect, right?
Yes, the curves never intersect. There's a unique curve, yes. Because if they intersected and they crossed paths, that means at this point, the tangent vector is both some x prime and x double prime. That can't be because you're given a unique vector field x. Okay, or you could say, well, what about this? Right? What if they have the same tangent vector at this point, but they diverge into other things? Okay, that can't happen either.
Sir, in the flow equation, d sigma mu over dt.
This one.
Yes. This x mu on the LHS side is a function of sigma, and how?
Oh, because the vector field, so as I move along the flow, okay, so that is as I'm moving along the curve t. So I started at the point x, and now I'm at the point sigma mu of tx. Okay, and now I want to know what is the change in sigma mu going to be as I move an amount dt. Okay, that is the RHS, which is the tangent vector to this curve. Okay, it's the components of the tangent vector to this curve. Now what we're saying is that this depends on what is the vector field x at this point. Okay, it's not the vector field x at this point. X is of course defined over the full manifold. So I need to specify x, but I need to specify x at this point, which is why it depends on sigma tx.
But it can, we can define it at point x.
You want to define this x at this point?
Yes, sir. Because we are defining slope d sigma mu over dt at point tx. So.
Yeah, so the point tx is this one.
Okay.
Right, this is the point x 0x, right, where t is 0.
Okay. Okay.
Right, so I want the tangent vectors to match as and as I'm changing points along the flow, my x is also changing, right, because I'm at a different point in the manifold. Okay. So now you can think of this flow, okay, as a one parameter group of transformations. Okay, so let me explain what that means. So let's consider a manifold M with a vector field X. Okay, and once we've seen that once you specify this vector field, it defines a unique flow function. Okay, the sigma, which is a function of T and X. And if I think about this sigma T, okay, that is if I fix the value of T, okay, so I'll just write this value of T here. Then what this does is I have a free slot here X where I can feed any point on the manifold. Okay, and what it returns for me is some other point on the manifold. Okay, which means if I look at my manifold, here are these integral curves. If you give me a point, okay, if you give me, let's say this point, then what I will do is I will flow an amount T for you and tell you what is the new point that you're at. Okay, but I can do this not just for this point, but I can do this for every point on the manifold, which means that every point in the manifold flows to a new point. Okay, so every point in the manifold will flow to a new point. Okay, this manifold doesn't have a boundary, so imagine that this wraps over. Okay, or it's infinite in extent. So this manifold, this mapping, okay, is now a mapping from the manifold to itself. Okay, and this mapping is a one parameter diffeomorphism. Okay, it's a one parameter diffeomorphism because it takes you, every point gets mapped to one unique point, okay, on the manifold. Okay, and this basically becomes a one parameter diffeomorphism. So the set of all possible functions sigma t now, okay, it forms, so if I change the value of t, that gives me the set of all possible sigma t's. Okay, so for this value of t, I end up here, but if I change the value of t, then I would end up here. Okay, if I, let's say, increase the value of t. So the set of all possible sigma t forms a continuous one parameter group of diffeomorphisms under composition. Okay, so what does that mean? So I have the set of all possible sigma t's. Okay, what does sigma t do? It takes a point on the manifold to another point on the manifold. Okay, and for this I have to specify the value of t. And the set of all sigma t's means that I take all possible values of t and I consider all these mappings. Okay. Now, if I compose two maps, okay, so let's say I compose sigma s and sigma t. Then we've already seen that sigma t compose sigma x is equivalent to sigma t plus s acting on x. Okay, that means that if I compose two of these elements, sigma t and sigma s, that returns for me a third element which belongs to the same set. Okay, so the set is closed under composition. Okay, which is one of the properties needed to define a group. Okay, the second is that if I take sigma 0 compose sigma s will be just sigma s. So sigma 0 basically acts as the identity element of the group. Okay, and similarly, if I have sigma t and I compose it with sigma minus t, then I will get sigma 0. Okay, so this gives me the inverse of the operation sigma t, and so sigma minus t is equal to sigma t inverse. Okay, so there's also an inverse element to this group of transformations. Okay, so this group is a very abstract group, right? It's a group of operations that I can perform on the manifold. For every choice of t, I get a different group element, and therefore it's a different operation that I can perform in the manifold. The result of this operation is that for every point on the manifold, it's taken to some other point on the manifold, okay, along this flow. Okay. Locally, the elements of this group are isomorphic to real numbers. Okay, that is because they're specified by a continuous parameter t. But this may not be true globally. Okay, for example, if you look at our transformations sigma t for the previous example that we did, where we had this kind of circular flow, okay, then we saw that if I transform by an amount sigma 2 pi n plus t, it would be exactly the same as transforming by sigma t, because this is like an angle of rotation. Okay, and so therefore the group sigma t is in fact isomorphic to just specifying an angle theta, okay, or an angle of rotation, which means it's actually going to be isomorphic to the group of 2D rotations, SO2, okay, which is the set of matrices which are parameterized by theta. Okay, so this set of matrices is in one-to-one map with the set sigma t. Okay, of flows defined by that vector field x which we had written down. So given a vector field x, we got a unique set of flows. Okay, the parameter t just tells me what is the angle that I've flowed. Okay, so for every choice of angle, I get a unique group element. Okay, and what does this angle do? Okay, if it takes points on R2, takes, for example, these points on this line, and it rotates them, okay, by an angle theta, by an angle t. With this angle is t. Okay, and it does this not just for these points, but it does it for every point in R2. Okay, it makes a rotation. So the entire plane is rotated by an angle theta. Okay, under this operation sigma t or sigma theta. Okay, and this rotation, again, it doesn't need a metric, right? It's just a transformation. It's just a flow generated by a vector field. Okay. Okay, let me pause for questions and I'll continue.
Sir, so one matrix representation of this group sigma t could be this, the same SO2 representation, like cos t minus sin t cos t.
Yeah, there's a one-to-one mapping between the sigma t's and this. Okay, but of course, if I want to think about how this acts on the manifold, I would not think of it by writing this matrix, right? Because
that acts on points on the manifold.
I mean, you could, right? You could think about this as, let me take coordinates x, y. So let me assign a point in R2. I'll assign it the coordinates x, y. Then sigma t is basically taking the point x, y, okay, which is a point on the manifold, and it's returning for me the points x prime, y prime, where x prime, y prime is equal to this matrix acting on x, y. Right?
Yeah, yes, sir. Like where the mapping then is sigma t composition phi inverse.
Composition.
Like patch, coordinate patch, like sigma t inverse, because this xy the coordinates are points.
Yeah. I mean, strictly, of course, you're right. This is an abuse of notation because we're, but we're suppressing that. We're using the coordinates interchangeably with the point.
Yeah.
Okay, so now let's consider a point x. Okay, so we have a vector field x on the manifold M, and we have a point x, and we'll consider so that uniquely. So once we specify the vector field x, it uniquely gives us a sigma. And now let's consider sigma epsilon, okay, acting on x. So that is, we're making an epsilon flow, okay, a small flow of this point x, okay, of any point x. So in coordinates, the sigma mu epsilon x can be written as sigma mu epsilon x, but I just pull epsilon inside, okay, to remind myself this is like a time that I can think of. And we so we know that we're trying to solve this equation, okay, with this initial condition. Okay, but we're trying to find, so at t is equal to 0, we're at x. We want to solve this equation and find where we are at t is equal to epsilon. Okay, that's what we're trying to do. So that's easy to do, okay, because since we're looking at small displacements in epsilon, okay, we know that we can approximate the solution to this first order differential equation. It's basically the initial value, which is x mu, Okay, and this initial value x mu is just sigma mu 0x. Okay, that's the initial value. Plus dt times this capital X mu. And this dt is epsilon. Okay, this is the little amount in t that we move. So it's epsilon times x mu of sigma mu tx. Okay, or sigma mu, sorry, 0x. Okay, so I mean, this is like a Taylor series expansion. Okay, so we're sort of getting to leading order in epsilon. Okay, or sorry, to first order in epsilon. This is the new coordinate that we will be at. Okay, so sigma mu epsilon of x, okay, is sigma mu 0x, that is the initial point, plus epsilon times x mu sigma mu 0x. Okay, I could have put epsilon here, but instead of putting epsilon here, if I'm only working to leading order in epsilon, I might as well put t is 0 over. Okay, so in simplified notation, this initial point is just given coordinates x mu, okay, which is the same as this initial point. And this point is epsilon x mu of x, okay, because this is x again. So therefore, the new coordinates, okay, of where we will be after an epsilon flow will be the point where we started plus epsilon times x mu. Okay. Under an epsilon flow, the coordinate changes by an amount epsilon times capital X mu. Okay, where these are the components of the vector field x that we were given. So what we say is that the vector field x generates an infinitesimal displacement. Okay, that is, if you give me an amount epsilon, I will generate for you a displacement of coordinates. Okay, which will take me from some coordinates x mu to this new coordinate sigma mu epsilon x. Okay, we were using this, through the GR course, right? We were saying that we can think of vectors as generating a concretely how it's realized. Okay, this is concretely how it's realized. The important point is that x mu really only gives you a direction of displacement. You need to specify the parameter epsilon to tell me how much displacement you actually are generating. Okay, and this is true for small displacements. Okay, that you have this approximation. Okay, so x mu by itself cannot give you a displacement. You need to specify as how much. Okay, but this x mu itself can be thought of as the displacement per unit epsilon. Right. Again, in the same spirit of thinking about this as a velocity, right? Velocity doesn't give you displacement. I also have to specify the time interval to tell me how much I flow. Okay? And for small flows, okay, it's just v delta t. Okay, this is like v and this is like delta t. This is the little bit of time that we flowed for. Okay, so this x is called the infinitesimal generator of the transformation sigma t. Okay, so x generates this transformation. So now we could ask, well, what happens for a large transformation t? Okay, if our transformation t is not small, then how would I solve this? Okay, and the claim is that in general, okay, we will write something like this: sigma mu tx will be an exponentiation of tx acting on x mu being the initial point that I'm at. Okay, so let's see how this is realized. So if I actually solve the differential equation, okay, what I will get is sigma mu tx is equal to x mu plus t. So as a full Taylor series expansion, okay, I'm writing out this sigma mu tx. This is equal to the initial point x mu plus t d by ds of sigma mu sx at s is equal to 0. I'm just writing a Taylor series expansion of this in t. Okay, and then plus t square by 2 factorial d by ds square sigma mu sx at s is equal to 0 and so on. Okay, so this is Taylor expanded about the point where t is equal to 0, or I'm writing it as s is equal to 0. So I can write all of this in terms of an operator, which is 1 plus t d by ds plus t square by 2 factorial d by ds square plus so on, acting on sigma mu sx where I evaluate all of this at s is equal to 0. So first take the derivatives, then evaluate at s is equal to 0. And this entire thing can be written as an exponential of t d by ds acting on sigma mu sx evaluated at s is equal to 0. So I've exponentiated this operation of taking of t times d by ds, okay, of sigma mu sx. And this is in shorthand, this is what we're writing as exponential of. So after I differentiate, then I set s is equal to 0. So in shorthand, we're writing this as taking d by ds, okay, is taking this d by ds of sigma mu. Okay, this d by ds of sigma mu must satisfy this equation. Okay, this d by ds or d by dt of sigma mu must satisfy this equation. So it must give me x mu. Okay, it must give me x mu, and this x mu evaluated at sigma mu sx. Okay, so it's the vector field at the point sigma mu at s. Okay, so in a shorthand notation, this is the vector field at. So all I did was replace this by x, or d by ds of sigma mu. I replaced it by the operation x. Okay, so in shorthand, it's written as exponential tx acting on x mu. Okay, but really you have to remember that first I take the coordinate sigma mu sx, then I differentiate with respect to s. Those differentiations are the same as the vector because d by ds of sigma mu is equal to x mu. Okay, sigma mu sx. So in shorthand, this is what we have done. Okay, so this is the way we write it out. So this flow sigma, okay, satisfies the following properties. Okay, sigma 0x, that is, if I displace by an amount 0, that just give me the initial point, which I can write as exponential of 0x times x, which is just the initial value. If I want d sigma by dt, okay, then I would just differentiate this equation, okay, and what I will get is x times exponential tx x, okay, or I can write it as d by dt of exponential txx. Okay, and the sigma t sigma sx, so this composition map can be written as first I will generate a flow by an amount s, then I will generate a flow by an amount t, okay, which can be thought of as a composition of two exponentials, okay, which is exponential t plus s x x, and this is the same as sigma t plus s x. Okay, so the important point is that the sigma, it can be thought of as an exponential operation, okay, by an amount t, okay, with the operation x, okay, acting on the point x, okay, and this x is basically, this capital X is the vector field, which is generating displacements in small x. Okay, I guess that's it for today. So any questions?
Sir, like, is this the reason why Lie groups are manifolds?
Is this the reason why Lie groups are manifolds? Yes, I mean, actually, okay, it's related. But it's a little more complicated than that. So a Lie group is sort of a manifold. Okay, and the Lie algebra is, so so when you say it's a manifold, okay, it's basically all the group elements are being assigned to points of this manifold. And so there is some identity element, which is some point in this manifold. Okay, and yeah, I mean, okay, we can maybe go over it at a later point, but okay, so roughly you're allowed to have a tangent vector space at this point. Okay, and so there is a tangent vector space at this point. These tangent vectors. Okay, so there's a tangent vector space at this point. But the other thing about this manifold, when you have a group, is that there's another important property. That is, you can define an operation, which is group composition, which is given two elements, G1 and G2. I should get a third element of the group. So there is an operation of composition which is not associated with all manifolds, which is associated with groups. Okay, whereas G1 composed G2 gives me a third element, G3. Okay. Um, if you apply this rule, okay, so if someone tells you what the composition law is for all elements on the manifold, then what you can do is you can apply it for infinitesimal elements, that is elements which are generated by infinitesimal displacements, okay, near the origin. Okay, and these infinitesimal displacements which are generated by these, so these are called small group elements, okay, which are group elements which are close to the origin or near the special identity element. And those small group elements, then the coordinates of those small group elements, I can think of as taking a displacement by an amount epsilon in some particular direction. Okay, so I have to pick out a particular direction. Okay, so this is, let's say, I'm specifying what the x mu's are. Okay, so if I specify the particular x, okay, that is I pick out one particular direction. Then what I'm going to do is I'm going to generate a displacement, okay, of every point on the manifold, okay, by picking out well, okay, at least at this point I can think about the displacement that I'm generating. Okay. It's okay, so it's a little more complicated, but suppose I have two such group elements, then the composition law of these infinitesimal group elements, okay, when I consider infinitesimal group elements, that translates into a relationship between these tangent vectors. Okay, the tangent vectors x1 and x2. So x1 is the tangent vector that I needed to displace by to get to G1. X2 is the tangent vector I needed to displace by to get to G2. Okay, and x1 and x2 will satisfy a property called the Lie algebra, okay, which will be related to uh, uh, there's some operation called the Lie bracket, okay, which you can define, which we'll do in the next class, in fact. And this Lie bracket will give me a third element, okay, x3 vector space. So G1 composed G2 will be related to G3, and roughly speaking, the Lie bracket of x1 and x2 will be related to the direction that you have to displace in to go towards G3.
Sir, yeah, in the example that you showed, like that, there was no constraint on the dimension of the manifold. It was just an arbitrary manifold. So, sir, like we saw that a capital X, the flow defines that is the like the generator of group element sigma T. So, sir, but there we only have one x. So, like, why do we have one? Like, then we'll not have any Lie algebra.
No, but there's a Lie. Okay, so for every vector that you pick out, every vector field you pick out, you'll get a different flow. Okay, the Lie algebra has to do with the non-commutativity of different flows. So if I pick out two different flows, they may not commute with each other. That we'll discuss this in the next class, not in the context of groups, but in general for arbitrary manifolds. Okay, the non-commutativity of two different flows. That is, if you give me a vector field x and a vector field y, the fact that these two flows don't commute is what gives you a Lie algebra.
Okay, sir. Okay. Thank you.
Okay, let me just stop the recording here.